Now, we've all been introduced to calling conventions when we use a telephone. Perhaps you answer yellow or ahoy hoy, as was favored by Mr. Burns and actually the inventor of the telephone, Alexander Graham Bell. Einstein answered the phone Einstein, and Koreans answer the phone yabaseo. Well, for this class, we've got conventions for calling of functions, and there's three elements of importance. How values are returned from called functions, how values are passed from called functions, and the register conventions of which registers can be smashed or should not be smashed when you call to a function. I'm going to start with the easiest one, how they're returned from functions. So we've already seen this. We've already seen main returning 41 or scalable. And later on in the class, we'll actually see returning values like a 128-bit integer, which can't even fit into a single register. But we learned before that the return values are returned in the A0 register. And I will tell you for the future that if you have some value that's too big for a 64-bit register in 64-bit code, or too big for a 32-bit register in 32-bit code, then the A0 and A1 register will be used to pass, with the least significant bits going in the A0 and the most significant bits in the A1. Now, where does this come from? This comes from the RISC-V ABI documentation, which tells us that the base integer calling convention provides 8 argument registers, A0 through A7, and their argument registers, but the first 2 of which are also used to return values. So I started with how to return values rather than how to pass values, just because it's simpler. Check, and we're done. Now let's focus on how to pass values into functions. Arguments are passed into functions using that thing we just saw right there. A base integer calling convention provides 8 argument registers, A0 through A7. But that doesn't exactly tell us which arguments are passed in which order. So I'm going to tell you that things are passed from left to right, A0 to A7. Concretely, let's say you were calling a function and it took 10 possible parameters. Well, the 0th parameter would go into A0, the 1th into A1, and so forth, all the way up until A7. So these first 8 parameters directly from left to right go into the corresponding registers. But what about those remaining values? What if you have more than 8 values passed into a function? In that case, the extra arguments are going to be passed on the stack. So 88 goes here and 99 goes here. So basically it's going to be from left to right. The leftmost values will be at lower addresses and the rightmost values will be at higher addresses. We don't even know what that is yet. We'll see that later on in this section. So under normal circumstances, of course, most things don't take 10 arguments to a function, so most of the time you're going to get away with passing arguments in registers, but sometimes they will be found on the stack. And where does that information come from? Well, going back to the ABI document again, it says that scalars that are at most xlang bits wide are passed in a single argument register or on the stack by value if none are available. I didn't highlight it, but I'll also point out that when passed in registers or on the stack, integer scalars narrower than xlang bits, so if we're in 64-bit code and we're passing a 32-bit value, or in 32-bit code and passing a 16-bit value, scalars that are narrower than xlang bits are widened according to their sign, meaning that if it's a signed variable, it will be sign extended with all 1s in the upper bits, and if it's unsigned, then it'll be all 0s in the upper bits. Widened according to their sign up to the type of 32 bits, and then sign extended to xlang bits. All right, there's an additional little bit of information elsewhere in the ABI that says the stack grows downward. We know that already. We've seen that already. But the first argument passed on the stack is located at offset 0 of the stack pointer on function entry, and following arguments are stored at correspondingly higher addresses. So that's what I was just showing in that diagram. 88 was at a lower address and 99 was at a higher address. Now there's actually a whole bunch more rules in the ABI documentation, and we will see all of the rules that I've just told you about in our examples, and later on in the class we'll teach you how to read the fun manual so you can come back and enjoy the ABI at your leisure. So that's how values are passed to functions, just the argument 0 through argument 7 and the stack if necessary. Moving on to register conventions of what belongs to what. So there's a notion of callee save registers and caller save registers. And the way I say it is that a callee save register actually belongs to the caller. Consequently, if the callee needs to use these registers that notionally belong to the caller, then it's the callee's responsibility to save the values so that it doesn't break anything for the caller. Basically, the caller should just depend upon the fact that certain registers will not be smashed by the callee, and that it is the responsibility of the callee to save and restore them so the caller doesn't know that they even changed. Another way to put this, and the way that the RISC-V ABI documentation says it, is that callee saved registers are preserved across procedure calls. So you've got some set of registers, and you call a function, you return from a function, they should have the exact same value. But the way that that's actually achieved in practice is that when you call into the function, the callee saves them if necessary. If it doesn't touch them, then it doesn't have to do anything. But if it needs to, then it needs to save and restore. So concretely, the callee save registers in RISC-V ABI is S0 through S11. So the S was save registers. So S0 through S11 and stack pointer. And again, the documentation says S0 through S11 shall be preserved across procedure calls. But I think this ABI mnemonic guide was the most helpful thing for consulting of, is something callee saved or caller saved? So specifically, if it says yes in the preserved across calls, then that is a callee saved register. Of course, it also just helpfully says right here that the S for the callee saved registers is a callee saved register. But looking at the yeses in this column, we also see the stack pointer. So the stack pointer should be preserved by the callee if it needs to change it, which of course most of the time it does. Most of the time, if it needs to change it, it must save it and then restore it at the end. And we've seen that multiple times throughout this class already. So those are callee save registers, so everything else must be a caller save register, right? Basically, yes. So caller save registers, they belong to the callee in some sense, and therefore it is the caller's responsibility to save the registers before it calls to a subroutine, and if and only if it needs to ensure that they don't change, and then it has to restore the register after the call returns. And the RISC-V ABI says that caller save registers are not preserved across calls. So concretely, it is the temporary 0 through 6, T0 through 6, and argument 0 through 7, and the return address, which are caller save registers. So circling it, we've got the temporary registers. So those are temporary, and the caller should not assume that the callee isn't going to use them. The callee may need some temporary registers of its own. So if the caller wants to make sure that the callee doesn't smash them, the caller needs to save and restore them before and after procedure calls. Again, looking at the no's in this column, we also have those argument registers, A0 through A7. We talked about how argument 0 and argument 1, A0 and A1, are actually used to return values. So this kind of makes sense then that argument registers, they are set before calling into a function, but the caller should not assume that they're not going to be changed. Indeed, the A0 and A1 will be changed if there's any sort of return. And just in general, the ABI says these are not preserved across calls. Therefore, the callee can use these sort of as temporary saved registers if they'd like as well. And indeed, we actually see that GCC seems to have a real thing for using things like A4 and A5 as its temporary scratch registers. Looking for more no's in this column, we also have the return address. So in this section, we're going to be focusing on calling to functions, so we're going to see a lot of usage of the return address. And so now we've seen all the caller and callee save registers. We've got 0, which is neither because it's always hard-coded. And then the ABI defines the global pointer and the thread pointer, which we said we don't actually really see the usage of in this class as unallocatable. So essentially, we don't know whether those are treated as callee or caller save registers, and we don't care because we're not actually seeing them in this class. The key principle, though, with callee and caller save registers is balance. Keeping things balanced as all things should be. Ultimately, both the caller and the callee are responsible for balancing any saves that they do, where here a save means storing something on the stack. If you put something on the stack, you better remove it later on. And that is ultimately the register calling conventions of what belongs to what. So these are the principles, and now we're going to see those principles in practice as we go through some examples of calling to functions. First without any arguments, then calling multiple functions, then calling functions with arguments, and ultimately we'll see bits of this. Now I will say that for the register conventions around caller and callee save registers, we're not going to see too much of that because actually there are plenty of registers. That's one of the benefits of having 32 registers total, is that in general the compiler has plenty of registers to juggle temporary values before, as it needs to calculate things and ultimately save values to memory. We are running mostly very simple code. Consequently, there's not too much juggling going on for the compiler, and very infrequently will we see the explicit use of caller and callee save registers, other than some of those special cases like stack pointers and return addresses.